Hi, I'm Artur Izmaylov from University of Toronto, and in my group we study effects of geometric phase in non-adiabatic dynamics in presence of conical intersections. Here I would like to present you the case where conical intersection modifies significantly the nuclear dynamics for the low energy wave packets that travels close to the conical intersection. Geometric phase effects become relevant when you have conical intersections, and this is quite frequent case in molecules. Here I would like to show you that actually conical intersections, they can modify dynamics of nuclear component, nuclear wave packet, even when the nuclear part has really low energy. So it moves mostly on the lower electronic states. And the conical intersections, they won't stimulate the transitions here, but through geometric phase effects, they will modify quite profoundly the dynamics of our systems. Now, the simplest possible model where we can have conical intersections is two-state, two-dimensional linear vibronic coupling model that has the following Hamiltonian. It can be thought as just two states, donor and acceptor, and they are parabolas essentially, or paraboloids in two dimensions that are shifted in energy and in configurational space, and also they have linear couplings that give rise to conical intersection when we diagonalize this potential matrix, right? So then close to the intersection, these two states, they look like this, and the coupling look like that, and so when we diagonalize this matrix, we obtain these conical intersections. To investigate geometric phase effects in this model, we will be looking at three methods: exact nuclear dynamics that incorporates both states and geometric phase, and will be done in diabatic representation, but then results will be transferred back into the adiabatic representation to be able to compare them with results of two other methods, which is Born-Oppenheimer method, where our nuclear dynamics will be evolving on a single electronic state, right? And the Born-Oppenheimer dynamics will neglect all the geometric phase effects. And then the third method will be Born-Oppenheimer plus geometric phase, where following the Mead and Truller method, we will include the geometric phase effects, but we will stay on the lower surface and see by comparing the two methods how the geometric phase effects will alter the dynamics. And comparing the results with the third method, we will see how the presence of the upper state modifies the dynamics as well. To give you a little bit more details on how do we exactly do the exact diabatic dynamics, I'd like to put a couple of equations here so that you can really easily go and do it at your convenience, right? So we have diabatic Hamiltonian here that consists of kinetic energy part and the potential energy part. The potential energy parts are very simple. It's again these paraboloids, and we can build the matrix of this Hamiltonian in, say, harmonic oscillator basis. And then to represent our results, we will switch to the adiabatic representation, right? And in adiabatic representation, diagonalizing this potential matrix gives us two potential energy surfaces. They have two wells that are separated by the region of conical intersection, and we will be monitoring the population of the, say, initial well where we put our localized wave packet, and we'll see presumably the dynamics to the other well. Now the equations we solve still in diabatic representations are this two-component nuclear Schrödinger equation for the nuclear wave function. And once we solve that equation, we can transform all our results to adiabatic representation to compare with the other methods. Okay. Now in two other methods, Born-Oppenheimer and Born-Oppenheimer plus geometric phase, we work solely in adiabatic representation. So we have potential terms from our diabatic model. We only focus on the lower state, and Born-Oppenheimer nuclear Hamiltonian will have kinetic energy, just the square of the nuclear momentum, and the lower surface. Now in third method, where we include the geometric phase, we use Mead and Schuller method, where the momentum is modified by including the geometric phase factors, and that gives rise to some extra terms that will change the dynamics eventually. Now, these are the ways we include the geometric phase, and in this diabatic model we have, it's particularly simple. We just put the diabatic potentials in the theta equation, and the theta can then be differentiated with respect to nuclear coordinates. Now, the equation we solved for both of these methods is the nuclear Schrödinger equation, but just a single component version of it, because now we have only one state to consider. Okay. All right, so here is the main result of our investigation, because if we, from the initial setup, reverse it in the vertical configuration, and so we have two wells, one at the bottom and one at the top, separated by conical intersection region for, say, Born-Oppenheimer and Born-Oppenheimer plus GP methods, then we can propagate and see how the nuclear dynamics will evolve. As we would expect in Born-Oppenheimer, the wave packet will tunnel below the region of conical intersection and will appear on the other side. Now, what happens when we add geometric phase in this problem? Well, really not much happening. The tunneling is frozen, which is quite surprising if we think quantum mechanically. Usually the tunneling is hard to avoid. Okay. Now, if we plot the population of the initial well as a function of time, and some of the details of this given in the paper cited below, we can see that the coherent oscillations of Born-Oppenheimer in black, they are, well, represented in this sinusoidal plot. But when we add geometric phase, the blue population line is constant, and it stays in one well. And that blue line is almost exactly on top of the exact red line that also constant. And that shows us that actually Born-Oppenheimer plus geometric phase captures the physics of this problem quite nicely, and we do not need to care about the transition to the upper state that are possible in exact method, but in this case they don't matter at all for the dynamics. Now, a simple way to understand this result is to think about the tunneling as a process that has two pathways below the transition states in this problem, and these two pathways, they acquire two different geometric phases, and when they meet on the other side, they destructively interfere. Note that dynamical phase in this problem is exactly the same, and so doesn't affect the dynamics at all, because the dynamical phase, due to the symmetry, will be just exactly the same for two pathways. But geometric phase is going to be different, because going on the left and on the right hand side of the conical intersection will produce different signs of the geometric phase. And in a sense, this is very similar to commonly known experiment, double slit experiment, where we have zero intensity of the light going through the two slits because of the destructive interference of the pathways from the two slits. Okay. Now, another question I would like to address is how relevant these simple considerations to our real molecular systems. And the answer, of course, to this question is quite relevant. There is a whole class of systems, so-called Jahn-Teller distorted systems, where we can have conical intersection between the two configurations, and the presence of conical intersection may affect the dynamics between the two configurations. And the simple example I would like to consider in this case is so-called bis-methylene adamantane molecule, or cation in this case. And in this cation, we can have a very symmetrical configuration, D2D symmetry configuration, the low energy of which can be lowered by distorting the symmetry of the problem. And we have two distorted configurations where the charge is on the left or on the right of the molecule. Then the conical intersection is right between these two wells. And what is interesting is that the Born-Oppenheimer barrier, or barrier on the lower surface, is much lower than the 0-point energy. So naively thinking, you could assume that there will be transitions going on between this configuration of the molecule and that configuration of the molecule. Now, indeed, that's what we see if we plot again the population versus time of the well. And in Born-Oppenheimer two-dimensional effective model that we explain how we construct in this paper, then we have these coherent oscillations that are going between the two wells. But when we add geometric phase, or we switch to the exact results, red and blue, we can see that the transfer is again frozen, and there is no transfer between the one well and another well. So if we put molecule in one configuration, it will stay there forever. Now, these results are also backed up by calculations of full dimensional 78-degree of freedom linear vibronic coupling model that we've done using perturbative methods. Now, it's not always possible to freeze tunneling in the systems, because if you play with the barriers height, you can engineer the model where both Born-Oppenheimer and Born-Oppenheimer plus GP will have a transfer. But what is interesting is that geometric phase still has a nice hallmark of this line of destructive interference on the other side. And it's quite visible in these simulations. Also, what is interesting, even if we lower the barrier, since the conical intersection is still up in energy, the transition to the upper state is not very relevant, and that you can see comparing the population plots versus time for the case with Born-Oppenheimer, Born-Oppenheimer plus GP, and exact. You can see that exact and Born-Oppenheimer plus GP, they are very similar in this case, while Born-Oppenheimer is quite off after the initial time. Now, one way to suppress the destructive interference would be potentially to make these two pathways around the conical intersections not equivalent. And a simple way to do that is to add some extra terms into the Hamiltonian that makes the transition states in these problems different in energy. So then the conical intersection is still in between the two wells, but it's somewhat on the slope, and as you can imagine, the transfer from one well to another through the lower pathway will happen more frequent than the than wave packet following the transition state over the like this high barrier, right? And that's indeed the case if we simulate this asymmetric setup with Born-Oppenheimer and geometric phase, and Born-Oppenheimer without geometric phase. The dynamics, just the way wave packet evolves in time, it's very similar and visually almost indistinguishable. Now, if we plot the population versus time again, in these dashed curves we have asymmetric setup, and as you can see, there are some small differences, but qualitatively the blue and black, blue being the with geometric phase and black without, they are quite similar. While in symmetric setup, as we saw before, the dynamics is qualitatively different in these two cases. Now, we can safely say if we make the distinction between the two transition states high enough, then geometric phase can be ignored in this problem. To summarize, I would like to say that presence of a conical intersection modifies even low energy dynamics. And the key to this modification is the geometric phase effects that are induced by the conical intersection. So the most important case we found so far was the dynamics in the Jahn-Teller distorted compounds, where if you don't account for the geometric phase, then dynamics will be qualitatively wrong. While you can suppress this destructive interference that happens because of conical intersection by changing the transition state energies. And if your system has different transition state energies, then you can safely ignore geometric phase effects.